We are Group 18. This is our final project. I'm Jason Lee. My student ID is 109610017. First, let's talk about why we choose this topic. At the beginning, we choose simple pendulum as our topic, but it's not creative enough. So we started to find what can we produce a field that causes a stable movement to measure time. So we still choose the pendulum. We are also curious about other kinds of pendulum that can intrigue us. We don't want to choose an electrically driven pendulum because then we think it's too normal. Then we found a magnetically driven horizontal pendulum, which impressed us very much because it connects and integrates the course in this semester. We have a voltage supply made in our electric experimental course. Therefore, we can easily get the materials to make the experiment.
Hello, I'm Ray Hu. My student ID is 109610018, and I'm going to introduce the components of our device. The first part is the pendulum part, and itself is a copper wire, so we can make sure that the current can flow through the pendulum after we conduct it. And the second part is the counterweight, and we choose to use a straw as our balance rod because we guess the size and weight of a straw is suitable for our experiment, and besides we can get it easily in our daily life. The third part is a tangled copper wire. We will tangle our copper wire into many circles, and it is an end of the pendulum that conducts the magnet. The fourth part is the pivot, and we'll wind the copper wire around the pivot. The fifth part is the axis. The axis part itself has to be a conductor, and we'll add positive supply to this end later in our experiment. The last part is the magnet. We'll add negative voltage supply to this end, and the magnet will produce a field that bounces off the pendulum later in our experiment. The next part is about how does the device work. First, we add power supply to both the axis and the magnet end, and after the device is conducted, the current should flow through the pendulum. Later, the repulsive force between the copper wire and the magnet will cause the pendulum to bounce off, and as soon as it reaches a certain height, the weight of the copper wire will bring down the pendulum again, and ideally, the pendulum can swing in a reciprocating motion. And this is our materials that we use in our experiment. There are magnets, enameled wire, rod, maybe a coat hanger, voltage supply, and straw and sandpaper. This picture is to show how our device looks like, and this yellow circle is the pivot, and below this yellow circle is the axis. The red part above is the tangled copper wire, and below is the magnet. And this picture is our voltage supply we made in our experimental course.
Hello, it's Tony Chu. My student ID is 1096100005. And this is our first build of this one. And we didn't put on straw because the balance rod is low enough and its weight is okay. Yeah. And we have done a Python movement simulation, the ideal one. We think it will move like cosine wave. Yeah, the reciprocal movement, reciprocating movement mentioned above. Yeah, and the real one, we think the wave will decay within time, just like damp oscillation. Yeah, but in the end we failed. There are some reasons because the magnetic field produced by the coil is not strong enough. We think there's not enough coil turns, and maybe the weight of pendulum is too heavy. And the last one, the fields of natural magnets are too strong. The magnets are this one and this one inside their magnet, and here is magnet, and the wire is here. Yeah, so we got our plan changed. Oh, and we will play the failed video. This is our new plans attempt, and the magnet is repulsive. Yeah, and when we turn on the voltage supply, we think it is because the magnetic field is not strong enough, so it cannot work like a ticker. Yeah.
Hello, my name is Albert and my student number is 1096100008. Our second plan is using ping pong to calculate time. And the material are ping pong and hair dryers. We use two different methods to measure the period. First is to drop the ping pong, and the second is set the ping pong on the hair dryer. We will use different hair dryers, and different hair dryers have different strengths, thus will affect the height of the ping pong.
It's Q again, and I'm going to introduce the Euler's equation of motion in fluid dynamics. And this is the equation. Yeah, low multiply g is the gravitational acceleration minus gradient pressure equals low multiply dv at d speed to t plus, and yeah, and fluids are hard to solve because the fluid velocity interacts with itself. Like the motion of the water at a point is affected by the motion of water nearby. Take an example. Yeah, these two components of velocity, u and v, two components just like x and y interact with each other. So indicating the equation of motion is non-linear, and it's hard for us to find a general solution. So we try to use simulation to get a solution. Yeah. And next, I'm going to introduce Bernoulli's principle. Yeah. For simple duration, we assume that the flow should be steady, incompressible, and viscous. And because of steady flow, so this one will reduces to 0. And then we choose a Cartesian coordinate with z component pointing upward, and use the identity shown below, and we can rewrite the Euler's equation of motions. We will get this, and we have to calculate the dot product with infinitesimal length ds in the direction of the flow line, and recognize that speed v is parallel to ds, and this will reduce to 0 because they are perpendicular to each other, so it will be 0. And final, we'll get the Bernoulli's principle. Yeah, shown here. P plus half of low speed square speed plus low gz. Yeah, and z could be replaced by h. And this is our flow result 1, which is use my drive. Yeah, and we use tracker to track the movement, and use MATLAB to simulate the height function. Yeah, and this is the video. And for results 2, and the final one.
5秒。
The last experiment is drop the ball from 15 centimeters tall, and we will get drop results like this. And here are the 3 videos. This is the end of our project. Thanks you for your listening.